US Physics Olympiad, year 2015, USAPHO. Problem A3. Solution for this problem you can find below this video in the reference of the description. A large block of mass MB is located on a horizontal frictionless surface. A second block of mass MT is located on top of the first block. The coefficient of friction, both static and kinetic, between the two blocks is given by μ. All surfaces are horizontal. All motion is effectively one-dimensional. A spring with the spring constant K is connected to the top block only. The spring obeys Hooke's law equally in both extension and compression. Assume that the top block never falls off of the bottom block. You may assume that the bottom block is very long. The top block is moved a distance a away from the equilibrium position and then released from rest. Question A. Depending on the value of A, the motion can be delivered in two types: motion that experiences no frictional energy losses and motion that does. Find the value AC that divides the two motion types. Write the answer in terms of any or all of μ, the acceleration of gravity g, the masses mt and the mb, and the spring constant k. Question B. Consider now the scenario when amplitude A much greater than AC, A critical. In this scenario, the amplitude of the oscillation of the top block as measured against the original equilibrium position will change with time. Determine the magnitude of the change in amplitude delta A after one complete oscillation as a function of any or all of A, μ, g, and the angular frequency of oscillation of the top block omega t. Question C. Assume still that amplitude much greater than AC. What is the maximum speed of the bottom block during the first complete oscillation cycle of the upper block? Solution for the first question. Maximum possible force exerted by spring on both blocks is Ka equal total mass of both blocks multiplied by their common acceleration when they stick together. It means that acceleration equal Ka over total mass. But this acceleration could provide for the bottom block only force of friction, which is maximum possible μ mass of the top block multiplied by g. So it means that critical amplitude we can find from this equation, where on the left we have maximum possible force of friction, and on the right we have mass of the bottom block multiplied by this acceleration provided by critical amplitude AC. From here we can find what is this AC. That will be this expression. And this is the answer for question A. Solution for question B. On this diagram it's easy to show total solution. If we have oscillation without friction, that will oscillate on a black line from rightmost position to the leftmost position. But if we have a force of friction, which is acting most of the time on the top block, we have position of equilibrium shifted by distance dx, which can be found from this equation. Dx equal force of friction by constant k. And this position shifted to the right from original equilibrium position. It means that when this block moving to the left, it will stop on a distance 2 dx to the right from original leftmost position. Now when it will stop, it start to oscillate to the right, but now this position of equilibrium is shifted by dx to the left from original position of equilibrium. It means that total amplitude, when it's moving to the right, it will be shorted by 3 dx, and it will stop by 3 dx less from this position of equilibrium. But because it's shifted by dx, total stop point will shift by 4 dx from the rightmost position. So it means that total amplitude will change by 4 dx. And solution for this question is 4 dx, which is 4 mil mtg over k. That's the answer for question B. Solution for question C. When top block moving to the left, it exerting force of friction to the bottom block during half of period of this oscillation for the top block, and period equal 2 pi multiplied by square root from mt over k, and the total time this block will accelerate bottom block is t over 2, which is this one. During this time, the top block will act with a force mu mtg on the bottom block, which accelerated with the amount of mu mtg over mu b. And now to find what is the total maximum speed in the end of this process, that will be acceleration multiplied by time, which is this expression. That's the answer for question C.